In this video, we're going to look at the Wilcoxon signed rank distribution, which is used in the signed rank test. So the setting is that we're in a one sample location model. Our data follows some unknown symmetric density with a unique median, and it's absolutely continuous. Okay, a couple videos ago I did a video on where we only knew that the random variable had a unique median and it was absolutely continuous. And here we're adding the idea of a symmetric density. So we're adding assumptions to the test. So the hypothesis that we're going to look at here is that is the median 0 or is it greater than 0? So then we take a random sample of our data, and since under the null the median 0, so it's we should see about half below and half above. But if we see too many above, that means that that's supportive of the alternative that the median is greater than 0. And one thing to note, which I find quite fascinating, is if the only assumption that we use is that the density is absolutely continuous, then there's no other reason to use any other test besides the sign test. It is the uniformly most powerful test when that's the only information we know. And in a couple of videos I showed that or proved it. But here we're adding the assumption that the distribution is symmetric. So we're going to add information. So in the sign test, we just looked at the number greater than 0. And if the number of observations greater than 0 got too large, that was supportive of the alternative. But in the sign rank test, they look at essentially how many are above 0. And they do that through the ranks, the absolute values of these ranks, which we'll show in a second, which is incorporating the distance from 0. So not only the number greater than 0, the number of observations positive, but also we're incorporating the distance from 0. So what we do is we take our original data, we take the absolute values of them, and then we rank them. Okay, which one's the smallest, which one's the biggest? So this may be the smallest, and that's the second and the third and the fourth and the fifth and the sixth. And so each one of these gets a rank from 1 to n. And then the test statistic is the sum of the ranks of the positive sample items. So some of these original x's will be associated with negatives, less than 0, and some will be positive. And we're only going to add the ranks of the ones that are positive. And so if we have too large a number of positive values, the ranks are going to be incredibly large. So we're going to reject the null hypothesis when the sum of the positive ranks, the signed ranks, are too large. So now let's look at a quick example here, or some more notation than an example. So if we let the absolute value of x, 1, so this is the, when you use a number in parentheses, that's we're ordering the data somehow. So this observation is the smallest rank, and this is the second, the third, the fourth. But this may be associated with any one of the observations. It might be our 10th observation, but happens to be the smallest absolute value. And this may be our first or 10th or whatever. So we're ranking these. Now we're going to create a variable if the jth rank is associated with the positive original value, then it gets a 1. Otherwise, it's a 0. So if this is the second smallest absolute value, and the original data was positive, meaning greater than 0, then W2 is a 1. But if this were associated with the negative value prior to taking the absolute value in the rank, then we'd get a 0. And remember, we're trying to add these ranks up. So the test statistic becomes this. It's the sum of j times wj. So this is when I is 1, this is 1. So then it looks to say, hey, was this a positive or negative? If it was positive, well, we want that rank. That's what it says. And then say on the third value, so j is 3. If this originally was positive, then it's 1 times 3, and we're going to add it in our sum. But if this was a negative, then w is 0. So it's 0 times 3, and we don't add it into our sum. And so notice that when we're adding a bunch of things up, the central limit theorem may apply. But that's not the goal of this talk. Maybe the next one. So let's do a quick example. Let's say we have 3 data points, and it's a random sample, and under the null hypothesis, the median is 0. So we some may be less, some may be more. Actually, they may all be higher than 0 or positive. They may all be negative. There's 8 possibilities. This could be a below or above 0, below or above 0, below or above 0. So to find the distribution of our test statistic, the signed rank, we have to look at all the possibilities, and that's what this does. So after we rank our data, so this is the smallest, this is the second smallest, this is the third smallest, they get a rank of 1, 2, and 3. So one possibility is that they all ended up positive. So our test statistic would be 6, 1 plus 2 plus 3. Well, we have to consider that maybe this one was negative and these were positive. So then our test statistic would be 5, 2 plus 3. Well, we have to do that for every possibility. And under every possibility, we get a test statistic. Okay, so here's the 8 possibilities. So now if we look at a distribution of the possible values, this is it. So this is the signed rank distribution for n equals 3. There's a 1/8 chance that they're all associated with the negative value. There's a 1/8 chance that they were all associated positive, and this is everything in between. We'll do one more, and then I'm going to illustrate this in R. So if we have 4 values and we rank them, rank the absolute value. So this is the smallest absolute value, second, third, fourth, and this. And then our test statistic is again this sum. So we're going to let the interiors here be the WJ. Okay. So this, if it's a 1, that means the original X, prior to taking the absolute value, was positive, so we get 1s. And so to calculate this test statistic, you take 1 times 1 plus 2 times 1 plus 3 times 1 plus 4 times 1, and we get 10. Well, since we have to go through all possible combinations, there's 2, 4, 8, 16 possibilities, that this is what we do. So here, this is associated with the negative, positive times positive, add the this times that, plus this times that, plus this times that, plus this times that, you get 9. Okay, and you do that for all 16 possibilities. So these are the WJs, and this is the ranks associated with our data, which ends up being the J. 1, 2, 3, 4. Well, here is all the possibilities, and then here's the distribution of the test statistic under the null hypothesis. So 1/16 chance that they were all negative, a 1/16 chance that they were all positive, and this is in between. So we can find the probability that T is, say, greater than or equal to 10. Well, it's 1/6. So now we can start developing hypothesis testes based upon the distribution of the signed ranks. Well, let's illustrate this on R.